Hello, welcome to the second part of this presentation. Now that we know a definition of the fractional derivatives, we're going to postulate a different definition using Clifford algebras or the algebras of matrices, right? So the previous definition attempted to define, right, the fractional derivative operator as taking as the differentiable functions in the real line onto the functions on the real line, right? However, it's a rather complicated definition, and for example, the fractional derivative of a real function, right, turns out to be complex. So it doesn't belong to the range anymore. So what is the range of the fractional derivative operator? That is to be determined, right? Because it goes beyond the real line, even though you started with something that's supposed to go into the real line. The answer goes into extension by scalars. Right? Let me write this down more carefully. So what we're going to do is consider this following Clifford algebra, right? CL over R of 1, comma 1, right? That is generated by X and Y, right? They're vectors, right? Such that, well, I'll just be more precise. It's generated by the 1 plus a vector x on the plane plus another vector y on the plane plus the wedge product of those two vectors, basically, right? So where the inner product of x and y is equal to 0, right? No, it's equal to 1 actually. And the inner product of x and x is equal to 0, and the inner product of y and y is equal to 0, right? So in other words, the metric from the Clifford algebra is given by that. So in particular, we get that x squared is equal to 0, y squared is equal to 0, x, y plus y, x is equal to 1. So, okay. Right. Well, actually, take that back. I'm gonna have to do this again. Well, it doesn't matter. Okay, so I got the Clifford algebra wrong, actually. So, yeah, so let's say it should really be the metric should be 1, 0, minus 1, right? So xy equals 0, xx equals 1, yy equals minus 1, right? So this means that this should be 1 and this should be minus 1, right? And xy plus yx should be 0, right? So what we're going to do is define the A operator to be x plus y over 2 and the B operator to be x minus y over 2, right? And then the nice thing about the A and B operator are the following, right? That A squared is equal to, in this case, it's going to be equal to x squared plus xy plus yx plus y squared, right? Divided by 4. So it's going to be equal, so this part is 0, right? Equal to 1 minus 1 over 4 is equal to 0, basically. Similarly, b squared is going to be equal to 0 as well. However, there's a nice property here, right? And the property is the following. AB plus BA, right? What is that equal to? Well, let's do the calculation and then we will be set. So this will be 4, right? So it will be x squared plus xy plus yx plus y squared, right? No, actually, take it back. I'm doing this wrong, actually. Let's just do it slowly so that we're able to digest it. So it's going to be equal to x plus y, x minus y plus x minus y, x plus y divided by 4, from which we get x squared minus xy plus yx minus y squared plus x squared plus xy minus yx, right? Plus y squared, right? Oh, this will be a minus y squared divided by 4, right? So we get some cancellations, right? This one cancels with this one cancels with that one. And not only that, right? I get, which is equal to 1 minus minus 1 less the y squared plus 1 minus minus 1 divided by 4, which everything ends up being 1. So kaboom, right? We get the following relationship, right? So a hat, b hat plus b hat, a hat is equal to 1. And I should be using a red marker, so because this is an important result, right? So this one and this one is also important too. So we have this Clifford algebra has two elements that are idempotent, and it has this nice relationship AB plus BA equals 1, right? Or the identity. Now let's do the definition of the fractional derivative by doing extension by scalars, right? So remember, we cannot use the functions of the real line as the range anymore, right? And there's no reason to believe that the domain of this fractional derivative operator is well defined on the differentiable functions because its image does not lie in the range of the original derivative operator, right? So we're going to have to extend the domain and the range into another space in order to make the fractional derivative well defined. And that's the plan, that's the idea behind extension by scalars, right? We're going to define the fractional derivative, in this case, the square root of the derivative operator, to be extension by scalars to the Clifford algebra, right? So Clifford algebra of 1, 1 R tensor product over R, so they're both algebras over R of the differential functions in R, right? And the range is going to be the same, Clifford algebra over R. So the scalars in this case are going to come from the Clifford algebra. We're extending the real scalars to scalars over the Clifford algebra. The scalars become a Clifford algebra in this case over functions on the real line, right? Now we claim that this operator is well defined. Now that we know, and we're going to show it, right? And as an aside, right, using bot periodicity, the Clifford algebra over the real line of 1, 1 is isomorphic to the 2 by 2 matrices over the real line. So the scalars are being extended to be 2 by 2 matrices, basically. Now we're going to define the square root operator of the derivative operator, right? So this is the definition, right? To be a tensor, the identity on this, right? plus b, right, tensor the derivative operator on this, basically, right? Basically, remember, we have a tensor product of algebras, right? The first operator acts on the first algebra, the second operator acts on the second algebra. So it's a well-defined operator, and this is over the real line, so over the real scalars. So this is going to be the definition. Now let's do a small calculation, right? To show that it works, right? But before we go on, right, let's consider this definition right here. There are 2 by 2 matrices, right? So A hat in this case corresponds to 0, 1, 0, and B hat corresponds to 0, 1, 0, 0, 0, right? So if you do this calculation, it satisfies all the solutions, right? So using the A and B basis, we get that, right? So let's calculate the fractional derivative of a function, right? In this case is going to be equal to A hat. So in this case, this is going to be equal to, so let's do it formally, right? The fractional derivative of the identity, right, tensor the function, right? And then we're going to do the application, right? So this is going to be equal to A hat times 1 tensor the identity acting on the function plus B hat acting on 1 times 1, right? In the Clifford algebra, tensor the derivative of the function, right? From which we get A tensor F plus B tensor F prime, right? In matrix notation, this is equal to 0 f of x, f prime of x, basically, right? So the derivative operator to the 1/2 of f is equal to 0 f of x, f prime of x, 0, right? Another way to look at it is matrix notation, right? So you get 2 possible answers. We get this one and we also get that one. Now let's go ahead and apply the operator to itself, right? So let's do square root square acting on f. That's going to be A tensor I plus B tensor derivative operator acting on A tensor F plus B tensor F prime of F, right? Let's do this one times this one, right? Then you get an A square tensor I acting on F is F, right? Plus AB tensor I acting on F prime is F prime plus BA tensor F prime of X dx acting on F is F prime of X plus B square tensor derivative of F prime is F double prime, right? Well, we know that B square is 0, right? So that cancels. We know that A square is 0, so that cancels. Now we're left with this part right here, in which we can pull out the AB and BA, right? So this is equal to AB plus BA, right? Tensor F prime, which in this case is equal to 1 because we did that calculation in the Clifford algebra, right? Acting on F prime of X. And lo and behold, right? Remember, yeah, so I made a mistake when I wrote this down, right? So this should really be the square of the derivative upper, something went wrong. Let's do it again. So the square of the derivative operator of the square root of the fractional derivative, right? Acting on a real function which is given by 1 tensor f, right? Gives me the derivative of the real function, 1 tensor f. So we have a well-defined operator, right? It remains to show that that any function, right, that well, that acts on the range, right, on the domain, any function that acts, if I put any function in the domain, I get a function on the range. That's what it remains to show, and that's what we're going to do next, actually. So